So, scan synthesis. So, in the scan synthesis, the one stage of it is scan configuration. So, in that process, so while mixing this negative edge and positive edge signals, positive edge scan cells in a scan chain, because the circuit, so it is having a negative edge scan cell followed by a positive edge scan cell. So, this is the circuit structure. So, we have, it has to be connected like this, because after this negative edge has come, so this value will be set to some proper value, and then in the positive edge the value will can be sensed by the next scan cell. So, they need to be grouped like this. So, the way it operates is that, so this is the scan clock that is running, and this is the x input, this is the SI, and this is the x, and then we have got y. So, suppose this, when this clock is going low at the negative edge, the value is put onto this x line. Then when this clock was going high, so this D1 value comes to this one. Similarly, this x gets the value D2 when this line is, this clock is going low at this point, and when this clock is going high, the next flip flop gets the value of D2. So, why you will take on the first x at the rising clock edge before x is loaded with the SI value at the falling clock edge. So, that will happen, but if we do just the reverse, if we put that positive edge scan cell before the negative edge scan cell, in that case both scan cells will always incorrectly contain the same value at the end of each shift clock cycle. So, what we say is that, suppose we just do the reverse, that is, we have got this one is positive edge triggered and this is negative edge triggered. So, what will happen when this SI value is given, when the positive edge comes, the value will be loaded here, and in the negative edge that value will be loaded here, but this flip flop will continue till still continue with the previous value. So, for some point of time both the flip flops will have the same value. So, what is happening is that the whatever value you put onto this D flip flop, so onto this SI line, so it will get loaded onto both the flip flops. So, whenever I have got two types of flip flops getting mixed, negative edge triggered and positive edge triggered, the design synthesis should always do like this, that the negative edge triggered flip flop should be put first and then the positive edge triggered flip flop, otherwise there will be problem. Then comes if there are two different clock domains, like, so this is the domain 1 and this is domain 2. So, in between we need to put a lockup latch. So, a lockup latch will be inserted between adjacent cross clock domain scan cells, in order to guarantee that any clock skew between the clocks can be tolerated. So, if there is a say clock 1 is driving this clock domain and clock 2 is driving this clock domain, so it may so happen that there is a skew. So, over the time the difference between clock 1 and clock 2, the time difference, it changes. So, if it change, then what we can do, so this the value maybe before it has been sampled by this clock domain 2 flip flop. So, it is this clock domain 1 is going to modify it. So, what is done, when this clock is low, so this lockup latch will hold the value, and it when this clock becomes high, so then this will remember the previous value. So, this lockup latch will be inserted in between whenever we have got this type of cross clock domain structure. So, in the some earlier example we have seen that there may be data transfer between clock domains. So, whenever we have that thing, so this scan synthesis process, it must introduce this type of lockup latches between the domains. So, here is that lockup latch sort of thing, like say clock 1 is this one, so clock 2 is this one. So, during each shift clock cycle, x will first take on the value of SI, whatever is there at the rising edge of rising CK1 edge, then Z will take on Y, okay, at the rising CK2 edge. So, that is going to happen, and Y in between, this Y signal in between, it will hold the value for Z to sample. Okay. So, this is, so you see that x has changed to the value D2, but this if this Y was not there, if this Y was not there, then this Z will get a wrong value. If Y was not there, this latch was not there, then Z will get a wrong value, because it has because of this clock edge skew. Okay. So, that has to be taken care of. Then at the RTL level, at the register transfer level also, so we can do something to enhance this testability. So, why RTL the RTL designs are needed? Like, so actually what is happening is that if we are talking at the gate level, then the number of gates in the design is increasing significantly as the designs are becoming more and more complex. So, number of gates are becoming increasingly high. So, there is a typical tremendous growth in the number of devices, then the timing becomes a problem. So, we do not have much time to put the product into market. So, in the introductory classes we have seen that the time to market is an important parameter. So, that has to be controlled. So, if we are going to test at always at the gate level, then we have to do much more testing compared to a higher level testing like at the RTL level. And there is a potential of yield loss. Potential of yield loss, like if I do not do RTL level testing, then we will have something like this, that some tests may get bypassed, and at the device level when you are doing, so some functionalities might not have been tested thoroughly. So, that way there may be some potential yield loss. Then low power issues, like at the RTL level. So, we know that we can so if the circuit is very big and we try to test the whole thing together, so entire part of the circuit will be getting power. As a result, there will be a lot of power consumption, but for a particular test pattern it may be targeted to test a fault in a particular region of the circuit. So, it may be sufficient to excite only that region, so give power only to that region, but this type of demarcation may be difficult to do when we have got a gate level circuit. So, when we have got a RTL level circuit, so since we know that okay, we have got this adder, multiplier, multiplexer, this is some decoder like that. So, we can target each of them separately. As a result, we may be having better power reduction. Then core reusability. So, this is another very interesting issue, because now most of the systems that we are designing, so they are based on this reuse principle. So, core are basically some pre-designed, pre-verified modules, so that are going to be integrated into the system. So, if we have got this cores, then we know that for testing a particular core, the core provider will give us the test vectors directly. So, what is needed is just to apply those test vectors to that core and get the responses and check them. So, because of this increased reusability, so we do not need to do test generation for these individual cores. So, as we are using this core based design, so our effort may be less from this point of sight, because we have just have to apply the given test pattern. So, test generation is not necessary. Of course, application may become a problem, we will see that later, but generation part at least is spared. Then time to market pressure. So, the overall time that we have in our hand is less. So, if we test at the RTL level, so maybe we are testing in terms of functionalities. So, if we are testing in terms of functionalities, so functions which are very much important, so maybe we test those functions thoroughly. Functions which are not that much important, maybe we just we do not do 100% testing of that. So, as a result, the time to market will reduce, and that will help us in getting better return from the product. So, design flow at RTL and gate level. So, at a gate level testability repair design flow will be like this. So, it will take the RTL design, it will go through a logic synthesis stage. After logic synthesis, we will get the gate level design. On that gate level design, so there will be testability repairs, that all those scan rules are there. So, all those repairs will take place. So, this process will go on. So, once we are through, we know that my design is it has been all the rules are being followed. Then we get a testable design. On this testable design, we do a logic scan synthesis, that will insert the scan chains and all that, and then thus we get the scan design. On the other hand, at the RTL level, if we do, so start at the RTL design, then we do a testability repair. So, we see whether there is any feedback loop and all that, whether is a gated clock and all that. So, all those things, but those tests are at the RTL level. So, we get the testable RTL design. After we have got this testable RTL design, we do the logic and scan synthesis. So, that is done, and that way we get the scan design. So, testability modules are inserted at the RTL level itself. So, RTL scan design rule checking. So, for fast synthesis, so they are mapped onto combinational primitives and high level models. So, we can since we want to do the synthesis process fast. So, we have got pre-designed modules. So, we just map the functionalities onto those high level model, and also combinational primitives that previously designed modules are there, we just put it onto that. But there may be testability problems. So, to identify the testability problem, we may have some static solutions, that is we just analyze the behavior, we just check the connection between the modules and all that, or there may be dynamic solutions. So, there we simulate the system and try to see whether it is creating any problem or not. So, this is one RTL level design. So, it says that this is some sort of Verilog code. So, at the positive edge of clock, if q happens to be all 1, then clock 15 equal to 1, else clock 15 equal to 0 and q equal to q plus 1. So, what is happening is that and at the edge of so this way it is actually counting the clock 15 value. So, after 15 clock pulses have been obtained, so there will be this d will get the start value. So, this is exactly what is happening. So, this clock comes, and this clock after this has become, this clock 15 line has become high. So, it will be acting as a clock for this d flip flop, and accordingly the start value will go to d. Now, the problem is that there is a asynchronous, there will be some scan problem in this, because now this in the test mode, what we do is that this if this clock 15 line is coming here in the test mode. So, it will be selecting, if the test mode is 0. So, it will be selecting this clock 15 line from here. So, it will be going into this d flip flop. On the other hand, if this mode is 1, then this clock goes directly to this one. So, in this case what is happening is that you see that this flip flop, when this clock 15 is low, clock 15 is not high. So, it is not getting any clock. So, we cannot put it into a scan, put it onto a scan chain, because this will not be this clock is different from this clock. So, what we are doing, we are trying to modify it, so that in a test mode the clock signal goes to both the flip flops, but in the normal operation mode, of course, this clock 15 will be driving the clock of this flip flop. So, this is modified. So, what is happening at the RTL level itself, the design is modified. So, we had this as the previously previous RTL code, and now we have got this as the new RTL code. So, it says that assign clock test equal to, so there is a condition check, if TM signal is low, in that case, so if TM is high, then it will be assigning clock. So, if TM is high, then clock test is getting clock. If TM is low, then clock test is getting clock 15. So, this correction that we want to be there in the circuit. So, that is that in the behavior in the RTL level code, we have that this line can be inserted. So, that is actually the RTL level corrections that is done by the RTL repair tool. Then this RTL scan synthesis, the scan equivalent of each storage element refers to an RTL structure. The scan chains are inserted into the RTL design. So, for every storage, the RTL structure will also have storage element. So, all those storage elements will be converted into the scan equivalent. So, all the flip flops that are there in the RTL structure, so they will be converted into scan flip flop. All the latches will be converted into scan latches. So, like that this RTL scan synthesis will convert all the storage elements into the scan structures. On the other hand, this scan chains will get created via this storage elements. Okay. So, this is RTL scan synthesis, and there is a pseudo RTL scan synthesis. So, this will specify the pseudo primary inputs and pseudo primary outputs, and it can cope with many other DFT structures, perform 1-pass single pass synthesis. So, we will see that. So, what is pseudo? We can specify some of the inputs to be pseudo primary inputs and pseudo primary outputs, and only for those flip flops or those inputs outputs. So, it will try to put them onto a scan. So, it is actually going towards that partial scan. Scan extraction and verification. So, scan extraction, it will rely on performing a first synthesis on the RTL scan design and generate a software model for tracing the scan connection. So, again the same thing, that is, it is trying to at the RTL description level itself. So, it will try to see where are the scan lines or where are the scan chains inserted. So, it is actually the lines that have been inserted into the description. So, corresponding to that, what will be the circuit that is synthesized, and this scan verification. So, it will rely on generating a flash test bench to simulate the flash test. So, flash test is basically checking all the scan chains. So, the scan chains, whether they have been fabricated correctly or not. So, that is tested by this flash pattern. So, this flash test bench will be generated, and to see whether this this is correct or not. This can be used for both RTL and gate level designs, because this is the scan chains are actually test. Then this then we apply the broadside load test for verifying the scan capture operation. So, broadside load test is applying the test pattern and seeing whether it is getting the value properly or not. We will come back to this when we go to the detailed testing, this BIST testing and all that. So, for scan capture operation of the RTL, this can be applied. So, DFT has become one of the vital tool for ensuring product quality. Scan design is the most widely used DFT technique, because that is now more or less accepted, that we have these scan chains are to be inserted. So, all these CAD tools that we have, so they are now supporting this DFT insertion technique. New design and test challenges that are coming up for this DFT design, for reducing test power consumption, then this test data volume and test application time. So, what is happening is that as the circuit is becoming more complex, so we have got this test data volume also increasing significantly. So, storing all those test data onto ATE is a challenge. So, that way we can try to do something by means of something known as test compression and all that. So, that this data volume is less, and application time also needs to be reduced. So, application time can be reduced by using many other techniques, like one is definitely reducing the number of test patterns, another is by transferring the test patterns faster from ATE to the device. So, that way, and of course, we need to cope with physical failures of the nanometer design era. So, more types of failures are occurring in the nanometer domain, nanometer era. So, those defects are to be covered by the fault models, and accordingly we have to come up with some DFT for those types of faults. Thank you.